Hello everyone. In the last few lectures, we have been discussing about resistivity logging tool, and we have discussed different types of tools and have covered the topic related to the application of resistivity log. There we discussed how the tool data is collected and how the tool data can be interpreted in terms of water saturation or identifying oil and water or gas zone. Today we will summarize the application of the resistivity logging tool, and I will introduce you to a new log which is called the spontaneous potential log. So in today's lecture, I will give you a synthetic log example of how a resistivity log looks like and what type of information can be interpreted by applying the knowledge that we have learned in the last few lectures. After that, I will give you an introduction to spontaneous potential log, and we will discuss what are the application of this log and how this log works. We know that an oil zone or gas zone, that means a hydrocarbon bearing formation or a rock which can contain oil or gas, will have high resistivity or less conductivity. This is because both oil or gas or all the hydrocarbons are non-conductive. They cannot carry the current, thus they will lead to high resistivity of the rock. Whereas a water bearing formation or a water zone will have less resistivity or high conductivity, only because formation water generally have good salinity and it will have what good amount of salt ion to conduct the electricity. But there could be cases where a water bearing formation might have very less salinity, thus high resistivity also. So we need to be careful about the interpretation of the formation fluid and must confirm with the other log also whether the zone have oil or water. Also, we have discussed that the decrease in porosity can lead to increase in the resistivity of the rock, because less porosity means less pore volume, that means less amount of formation water, that means we will have less salt ion to conduct the electricity, that will lead to decrease in the conductivity of the formation. Also, it will also lead to increase in the tortuosity of the rock, so current have to travel longer distance in order to flow. Then we have discussed about different types of tools. So we have a number of tools which could be classified on the basis of depth of investigation. So if you want to have a true formation resistivity measurement, that is the resistivity of the formation rock which is undisturbed by the invasion of mud filtrate. For that type of resistivity, we have to use a tool which have very high depth of investigation, or those tools are also called our deep resistivity logging tool. Similarly, if you want to measure the flush zone resistivity or the shallow zone resistivity, we have to measure the resistivity by a tool which have less depth of investigation, such as RXO tool or shallow resistivity lateral log tool. That is the we discussed in the last class. Those are implemented by the LLS in the dual lateral log. Also, what type of resistivity that we are going to encounter in the rock, it will depend upon what type of fluid type in the formation, as well as the our mud and mud filter type. So we have discussed that a resistivity profile exists inside the formation as we move away from the wellbore. So the resistivity profile, that means resistivity in the different zones such as flush zone, transition zone, or the invaded zone, and the true formation. It depends upon the what type of mud it is and what is the salinity of that mud and what type of formation fluid we have, whether oil, gas, or oil and gas and water, and what is the salinity of the formation water. When it's come to the quantity interpretation, one of the fundamental rock property that we can evaluate is the water saturation. So formation water saturation can be calculated with the help of RC equation by using the resistivity log data. But before we can use the resistivity log data, the tool data must be collected for the environmental effect. That is, all the tool data is called what? Apparent formation resistivity, and we must apply the Borel effect correction, adjacent bed correction, and the inversion correction to get the true formation resistivity RT from the apparent formation resistivity RA values. To give you an example, we have seen this figure earlier in the earlier classes. So we have a gamma log and SP log, which is basically tells us where you have scaly formation or a non-scaly porous and permeable formation. So from there you can identify that this is a porous and permeable formation. Now, what is the role of resistivity log data to interpret more about the formation? For example, you see here resistivity values are high, and you can see here we have three types of resistivity values. That means the tools that we discuss, deep lateral log, shallow lateral log, and the Arkshaw values, micro resistivity measurements, they are both present. So here they are represented in terms of deep reading, resistivity medium depth of investigation reading, and the shallow resistivity reading. That is, here it is Arkshaw. This is going to measure the true formation, that is the RT, and this is only up to the invaded zone. So somewhere between the RX and RT, that is the RI values. Now you can see the deep resistivity values are very high from here to here. So obviously that means if this is a porous and permeable formation according to gamma ray log and SP log, which we'll discuss in subsequent classes, how we can read the gamma ray log and SP log to find out where the porous and permeable bonded exist later on. So SP log and gamma ray log have told us that this is the boundary of porous and permeable formation, and within that boundary from here to here you have what? Very high value of resistivity of the formation. That means this must be a hydrocarbon bearing formation, and from here to here you have what? Very low resistivity of the formation. That means it must be a water bearing formation. And you can see the separation between the this deep, medium and shallow value is very high. It can only mean that the mud filtrate or the wellbore fluids are different in this zone from the formation fluid. Cell also generally looks at as low resistivity in this log. It, depending upon the type of shell and what are the formation fluid is contained the as terms of bound water inside the shell, its resistivity may be higher or lower, but it will be much lower than the our hydrocarbon bearing formation. Now resistivity log cannot tell us that this hydrocarbon is gas or oil. For that we need other indicator, such as we need the density log data. This is 5D density log data or the density porosity data, and this is the neutron porosity data. So basically by plotting neutron and density together, we can identify that this zone is our gas bearing formation and this zone is our oil bearing formation. Once again, we will discuss the use of neutron density, how we can identify a gas or oil bearing formation with the help of neutron density log later on. Also, if you recall, we have discussed several other indicators for identifying type of fluid when we discuss the mud logging. For example, we can use the fluorescence test. We can throw the ultraviolet light on the fluid sample collected, that is mud sample collected at the well site or on the well cutting, and see whether we are getting any fluorescence light or not. That will indication of an oil bearing formation. So if a fluorescence test is performed here in oil bearing zone, it will be identified as oil, and here it will be identified as a gas bearing formation. So this way we can correlate two logs together. From a history log we have got this is a hydrocarbon, this is a water bearing formation. We can correlate with the SPM gamma ray log in the first track, that will tell us okay, it is correspond to a porous and permeable formation. So this must be a or maybe a hydrocarbon bearing formation, and this may be a water bearing formation. Whereas if you further correlate with the density neutron cross plot, you can further delineate between the gas and oil bearing formation. So this was about our qualitative interpretation of these log data, and we can know that by looking the resistivity log data, the location of potential hydrocarbon bearing formation where the true resistivity RT data will read high values. Further, we can calculate the formation water saturation, this which is one of the main application of resistivity log, to calculate the formation water saturation by using the RC equation. So RC equation you can apply, that is so this equation can be used to calculate the formation water saturation. Also, we'll discuss later on different type of cross plot where RG equation can be solved graphically throughout a particular zone to give you not only the formation water saturation as well as the other properties such as formation water resistivity also. Generally, for example, like these two cross plot we will discuss when we discuss the well log interpretation in detail. Hengel cross plot and Pickett cross plot, where generally ratio data is plotted with porosity on a logarithmic scale on a XY graph paper. For example, we can plot RT and phi. We can take different data points from different zones and can plot them together, and we can identify the patterns and do the calculation on these patterns to find out what is the formation water saturation at different zones and what is our formation water resistivity, and it can also help us in identifying some other rock properties also. So once we have discussed all the porosity logs, we'll discuss this cross plot method for well log interpretation in detail. Now, another electrical log is spontaneous potential log. Earlier resistivity log data was used to calculate the formation resistivity. Now, spontaneous potential log is used to measure the naturally occurring potential inside the wellbore. So, a potential always exists inside the wellbore and current flows alongside the wellbore wall. So, we are going to measure this naturally occurring wellbore potential. This is one of the oldest log. This is one of the first log which were developed along with the resistivity log to be run inside the wellbore to find out the formation properties. So one of the primary application of this log is to identify a scaly formation with non-scaly formation. That means it can distinguish between a permeable formation such as sandstone, limestone or carbonate from a impermeable formation such as scaly formation. So we can define the bed boundaries. We can find out from where the shelly formation start, from where shelly formation ends, from where the porous impermeable formation start, at what depth the porous impermeable formation ends. Just like in our earlier figure, you can see that we have this black curve is the SP log. It tells us that from here to here we have a porous and permeable formation. Some other application of this log is we can also identify the what is the bed salinity. That means generally our, let's say for example, if I say that reservoir rock is, let's say, sandstone. So it is not necessary that sandstone will be pure sandstone. Sometimes scaly sandstone might be present. So we need to know that how much of the porous and permeable formation is composed of shell, whether 10% or 10-20% or 30%, because only the sandstone part of the our formation can contain oil and gas which could be produced. In scaly formation or the part of the our reservoir rock which made of shell, it will not have any movable oil and gas reserve. So we need to calculate the what is the saliness percentage in our rock to calculate the exact amount of reserve or correct amount of reserve inside our reservoir rocks. It can also aid in the mineral identification. It can also aid in the identification of deposition environment as well. And we can also use it to calculate the formation water resistivity as well. So to summarize, the SP log is one of the log which is used to identify the bed boundaries and calculate the bed thickness. And in the SP log, what we are going to measure is the what is the naturally occurring potential inside the wellbore. So in this figure, like you see, like against porous and permeable formation, generally SP log will going to give you deflection. Against a shelly formation or impermeable formation, you are not getting any deflection. So whenever in a SP log you see a deflection, that is an indication of that a porous and permeable formation might exist at that depth. So from here to here you have deflection from a straight line. So this is a potential porous and permeable formation. Now the tool construction, how the SP logging tool works. So basically what we have, the tool is very simple. We have two electrode. One electrode is at the surface and second electrode is inside the well bore which is moving. So we are going to measure this, the difference between the potential of the movable electrode in this well bore with respect to the electrode at the surface. So what is the potential difference between this electrode and that electrode that we are going to measure? Now the question may arise, why this potential exists? This potential exists inside the well bore because we have a number of formation fluids and the wellbore fluid which have different salinity. So this potential is existing only because the interaction between the formation coolant water, conductive diluent fluid, and the certain ion selective rock such as shale. So basically all these three elements which are responsible for movement of ion or the conductance of electricity. That means if a current have to flow, these three elements must be present. And if these three elements must be present, that means that this law can only be run in the conductive mud. If you use in oil based mud, oil cannot flow the current, so SP law cannot work in oil based mud. So generally it is measured in the millivolt because the value of the potential is very less. So maybe from few hundred of negative to positive, 100 around 150 millivolt. It is generally recorded in the first track along with the gamma ray log and the caliper log. So you can see here the scale is from minus 160 to 40 in this figure. So it is the first track. So we will have the red one is the caliper curve, the blue one is the our gamma ray curve, and green is our SP curve. It is not necessary to record both of SP and gamma ray log. Generally both are the logs, they serve the same purpose. The gamma ray log can also identify the bed boundaries and calculate the bed thickness. So depending upon the well bore condition, what type of reservoir that you are dealing with, what is the condition of the well bore, we can use either SP log or gamma ray log. So any of these log must be present to aid in the interpretation of other logs such as resistivity log, which is present in the second track, density or the different types of porosity log that are present in the third track. Now coming to the origin of spontaneous potential, as I mentioned that this potential exists because there are different types of fluid exist inside the well bore which have different salinity. So due to interaction between the our shelly rock, the formation fluid and the well bore fluid, our spontaneous potential exists. So this spontaneous potential exists can be clubbed into two components. One is the electrochemical potential, second is the electrokinetic potential. Electrochemical potential can be further classified into membrane potential and the liquid junction potential, or sometimes it is also called the diffusion potential. Generally the value of electrokinetic potential is very less. Only in certain conditions the value of electrokinetic potential or EK may be significant. Generally it is close to zero. That means the majority of the potential is our electrochemical potential, which is of two types, membrane potential and liquid junction potential. So let us discuss these two potential in detail, the membrane potential and liquid junction potential in detail. So we know that this is the basic concept that let's say we have two solutions. Let's say they are separated by a membrane which can allow the flow of ion. So we have weak solution where the concentration of ions are less, and we have a strong solution where the concentration of ions are high. Obviously ions are going to diffuse from a high concentration to lower concentration, and once the ion moves, so the current can flow. So this is the original condition. And the dynamic condition, the ion will be moving from strong solution or highly concentration solution to the our low concentration solution. This type of condition also exists in our well bore. We know that we have what mud filtrate invasion inside the formation. So here we have mud, here we have mud filtrate, here we have formation water or the coolant water, and here we have shale. So we know that the formation water and mud filtrate and mud will have different salinity. In certain cases they might have same salinity also, but for that to happen our RMF must be equal to RW. But almost all practical cases our mud filtrates or the mud salinity will be different than the formation water salinity. So what is going to happen after the invasion of the mud filtrate? We have different zones where the salinity contrast exists. For example, at the invaded boundary, we have what here, and on the right hand side we have Contd water, and the left hand side we have what, mud filtrate, which have different salinity. So obviously the ion diffusion is going to take place and the current can flow. So typically this is where our spontaneous potential will exist across the junction where cell and a potential porous and permeable formation meet. That means we must have a conductive boreal fluid, a sandwich porous and permeable formation between low porosity and impermeable formation, which is shell, and indifferent salinity between the boreal fluid and the formation fluid. So our impermeable formation generally cell, which is allows the movement of only a particular type of ion. So when the ions are going to move inside the wellbore due to different salinity, so ion movement is going to induce a current flow, or a potential difference will exist, or a EMF will be generated inside the across the wellbore wall. And what we are measuring? We are going to measure the potential of moving electrode inside the wellbore with respect to the potential of electrode which is at the surface. So let's start with the first potential. The first potential is our electrochemical potential, and as mentioned that it have two components, membrane potential and junction potential. Here at the boundary of invaded zone, here junction potential will exist, that is called EJ, and the boundary of the porous and permeable formation across cell, our membrane potential will exist, that is our EM. And total electrochemical potential is nothing but EM plus EJ. So EC is in most of the cases is the total potential inside the wellbore and the formation. So this is what the total potential, because EK is, as I mentioned earlier, generally it is close to 0. So let's discuss why membrane potential develop and why junction potential develop. Starting with the membrane potential. So what we have at the boundaries where shelly formation is separated from the our porous and permeable formation. In the non-invaded zone, what we have our Contd water or the formation water, and in the wellbore we have mud. So generally in most of the cases RMF is greater than RW, or we can say the salinity of the mud or mud filtrate is less than the formation water. That means formation water is generally more saline. So we will discuss generally this case, we will discuss all the example that the formation water is more saline compared to the mud and mud filtrate. Reverse could be the case, also be there inside the wellbore, and the results will be just simply the other way. That means the current action will be simply reversed. But right now let's discuss the condition where the formation water have more salinity. Since the formation water have more salinity and the mud have less salinity, so if this celly rock, it allows the movement of ion through its structure, then from higher concentration to low concentration the ion movement will take place. Here at this boundary, cell act as a cationic membrane. That means cell can allow the movement of cation or exchange of cation, because the cell have clay and which have layer structure which have negative charge and have difference of cation. So cell act as a cationic membrane and cations can move through it, whether an ion cannot move through it. That means in from the formation water, Na plus ion, let's say it is composed of Na plus NCl minus, Na plus ion can move through the cell because it is cationic membrane, it is allows the movement of cation. It can move from here to here. And why they will move from here to here? Because formation water have more salinity, it has more number of Na plus ion compared to our mud. So Na plus ion will move from our non-invaded zone to the mud, thus a current will flow. So that's why you can see here, if at the boundary we'll have the positive ions, because the positive ions are flowing in that direction. That's why we'll have EMF direction like this, because the positive ions are flowing in this direction. So direction of EMF or direction of potential which is being developed will be in this direction. So to summarize, membrane potential exists at the boundary across shell and the portion of permeable formation because shell acts as a cationic membrane. It allows the movement of cations from the formation water to the our wellbore, and a current will flow due to that, and a potential will exist. Now, second potential is our junction potential. The junction potential exists at the boundary between the inverted zone, that is this, and non-inverted zone. So non-inverted zone have higher concentration of Na plus and Cl minus compared to the our inverted zone, because we are considering again RMF is greater than RW, or formation water is more saline. Here both Na plus and Cl minus can move from the non-inverted zone to the inverted zone. Here what will happen is that since Na plus have large size compared to Cl minus, and it generally drags 4.5 molecules of water, whereas the chlorine ion have a smaller size and drag 2.5 molecules of water. Because of that, the Cl minus will have higher mobility. Cl minus will move at a faster rate as compared to the Na plus ion. That means overall there will be net influx of chloride ion from here to here. So here at this bond we will have a negative charge, here we will have positive charge. So that will the direction of EMF will be from positive end will be here and negative end will be here. So this movement of, due to this movement of chloride ion and Na plus ion, again a current can flow from the non-inverted zone to inverted zone. So this is about our electrochemical potential, which is made of two potential, that is the membrane potential and junction potential. In the next class, we'll have more discussion about the quantitative measurement about the electrochemical potential, and we will discuss about the electrokinetic potential, and then we'll discuss how to interpret the SP log data to find out where porous and permeable formation can exist, and also how to calculate the salininess of the formation and calculate the formation water resistivity.